I had to think a little bit about what I would be talking about, because Charlie gave me as a title Astrobiology project in Paris. So I thought I would summarize my talk as a Paris view on astrobiology. And that's tied to the fact that, in that PSL university, we decided to have some breakthrough and big science project. And one of the projects that came out of the big challenge today in science was a project around the origin and condition of emergence of life. So those are all the people involved at PSL that work on that project. It's a 3 + 5 years project with 500,000 euro per year. And we are trying to gather people from different communities, from physics and chemistry and biology within a virtual center to work on that big question of the origin and condition for the emergence of life. Here's my pointer. All right, so I decided for that talk to give a very low-key introduction to astrobiology, because the student audience is very broad. We have some high school students up to some PhD and end of PhD and postdocs, and some very nice speakers. So I decided to go very low so everybody can understand and start from there, and we'll be talking about it for the next 2 days. So one point of why I wanted to have some long break is, I think, to have 2 days of school plus 5 days of workshop with intensive lectures and no break and a lot of sun and outside is too difficult. So that's why I advocated to have long break in between talks and long lunch, because I'm French and it's a Franco-Australian workshop. So I think that's the first cultural exchange we should have. So what is astrobiology? So as you know, whether life is singular or multiple in the universe has been one of the big questions, a big science question, it's a big philosophical question since the beginning of time. People have been always wondering, what is life? How does it emerge? Why are we here? And you keep on going. So NASA put it out a nice definition of astrobiology with the Astrobiology Institute, saying astrobiology is the study of the origin, evolution, distribution, and future of life in the universe. We're talking both about extraterrestrial life and life on Earth. And astrobiology addresses, in fact, the question of whether life exists beyond Earth and how humans can detect it if it does. And I think for many years, astrobiology didn't get such a good publicity because it's very slippery field. It's very easy to go from a scientific question or philosophical question and slip into something that's murky and not clear what people are talking about. And I think it's now that we're starting to have data, both on exoplanet science and solar system and all different fields, it's important to think about how we can turn that into a real scientific question. And I think it's worth, starting a workshop on exobiology to remind everybody that, scientific process goes with making hypotheses, theoretical hypotheses, and most importantly, to validate that with experiment or observation. Without that, it's just speculation and philosophy. And if we're not very careful in that field to validate always those different hypotheses with experiment and observation, very quickly you turn into science fiction and are looking for whether those guys are over there. So clearly, why starting to talk about this? So is that long time questioning, and this is, the Greeks started to talk about it. Why should that be a field of interest, or why is that a new field, as Malcolm was saying, of interest? Is you have two revolutions taking place. On the one hand, you have starting to have a chemical understanding of living matter. We're starting to understand living matter at the chemical level and starting to probe very in a detailed way how the living matter works. And on the other hand, you have the discovery of exoplanet. Since 20 years now, we are discovering planets around other stars, and we have new data then on observation to test the various hypotheses we are putting forward. So as I mentioned briefly in my introduction, so at PSL, we decided to tackle that question around three main lines of inquiries: the astrophysics part, the chemistry and biology part, and we have maybe I will have time to talk about it. We also took into account the social science and art part, because it's also part of that field to talk about how we perceive life and how throughout time we change our perception of what life is and what extraterrestrial life can be. So on the astrophysics viewpoint, we don't really talk about the origin of life. We are, I think, more interested in the condition for the appearance of life, for the emergence of life in the solar system and beyond. From the chemistry and biology part, the big question is, how do you get to have living matter emerging from non-living matter? And it's a stepwise multi-scale process if you want to think about it in terms of a physical viewpoint. And what we have at PSL is roughly about 40 researchers, in 8 different institutions. PSL is a gathering of many historical institutions in Paris, small institutions, among them the Paris Observatory, but we have people from Collège de France and ENS and Institut Curie working on that project. So I'm going to go slowly, roughly today, talking about conditions for the appearance of life and what with the new data we have on exoplanet, we can start working on to try to decide whether or not there is life on other planet and whether, more importantly, whether we can detect it if we have biological activity on another planet.
Excuse me, Stephane,
yeah.
Are you having much success getting astrophysicists to talk to biologists to talk to the artists?
Yeah. Why?
Not all of us have.
Well, I can show you. So, I can show you if you want at the end how we do it, how we get those different communities to communicate. And I think it's mostly depend on how you ask the question. An astrophysicist is going to view that question from a certain viewpoint, and a chemist or biologist from another viewpoint. And the big question is, how do we work together to make experiments and try to validate hypotheses from one hand to the other? So I'm going to try to go through that process here to see, to show you how we're trying to do that. So first part, the astrophysical viewpoint. So So in the solar system, so origin and condition for the emergence of life, of course, this is what we know, life on Earth. Everywhere we looked at on Earth, you can see you have living matter, and there is 2 complementary data sets coming from, on the one hand, you have exploration of the solar system that has been going on for the past 50 years now, and we're starting to have some very good data on exploring the solar system and getting sample and studying sample. And something that those 2 fields are not that much talking to each other. You have the exoplanet science community that's starting to discover and characterize planets around different stars. So you have 2 complementary data sets that are very complementary in terms of they are looking at different things and need to be put it together. So if we look at the exploration of the solar system, so this is, the general view of the solar system that we have with 98% of the matter at the center of the solar system and a few percent along those different planets that go around the solar system. And for the past, so since the 60s, the beginning of the exploration of the solar system, we sent close to 200 probes. So sometimes it's hard to see. So there was a lot of failure. And if you look at the history of sending probes to the solar system, you see that in the 60s and 70s, they would get an idea, put it on the launch pad and launch it. 40 years later, the spatial technology is completely different and the algorithm is completely different. We spent 20 years thinking about an idea before sending it to space. And I think that we have changed the paradigm there. But anyhow, we have close to 200 probes that were launched. About 50% of them gather some data. And of course, we landed on the moon, Mars, and Venus. And what's important is we got sample data on those objects. And we have written sample only for the moon, but we landed on Mars, made some very serious measurement on Mars. On the outer solar system, we only have actually, out of those 200 probes, we have only a few probes that went beyond the asteroid belt. We have, of course, the Pioneer mission, the 2 Voyager mission, New Horizon, that just went to Pluto not that long ago, Cassini that plunged into Saturn, when was that? In this spring? September. And the Juno right now, that's measuring the gravitational moment of Jupiter. And I think it's important to remember that, in fact, we have limited data on the outer solar system. We just landed on Titan. That's the only place where we landed a probe and made some measurements. But we have sketchy data on our solar system. So we know quite a lot in the inside. And further you go, the more sketchy are the data. And one of the big discoveries, I think that's mostly understated, is there is no life recorded on the solar system except Earth. And that's something that wasn't obvious. You know, remember in the 60s where people were launching probes, they were very careful. They were sterilizing those probes because they were afraid of contamination. And I think we've forgotten that we were expecting to find a lot of bacterial and biological activity in the solar system, and at the end, we didn't find anything. So one of the big non-discovery of the solar system exploration is that life is not as much spread as we think, and is very concentrated on Earth. And right now, if we could find a fossil of a bacteria on Mars, I think it would make a huge news throughout the globe, while 50 years ago, people were sterilizing their probe because they were afraid of contamination. So we really have a shift of paradigm here. If we look at the architecture of the solar system, so people have been bothered quite a fair bit by that architecture, because we have big planet here, and you have some icy planet, and you have a different system inside, some asteroid belt. And for many years, people said, okay, that's an odd-looking system. It's dynamically not that stable. How did that form? How did we get those big planets here? And so right now, if you look at the probe that are, sorry, it's a bit crowded slide, but if you look at the probe that have been sent now to the solar system, you see that people have been sending many probes concerned with the formation of the solar system. So understanding the diversity of the planet, I mean, you almost don't have any planet resembling to the one to the other. If you look at the satellite, it's even worse. We have a great diversity of satellite. And we are sending still a few probes to around planets, but people are pretty much interested to understand and get information on the formation of the solar system, like the Rosetta probe that went around the comet to try to make analysis of the material you have on the comet to try to decide whether or not this was a big contributor to the water we have on Earth. There is a Dawn probe that's going to come around some asteroid in 2018 that's going to look at 2 different protoplanet or asteroid to try to understand planet formation. And of course, we have Mars 2020, and inside they are going to probe the inner Mars and try to decide whether or not, we had some water on Mars at some point. And also the Juno probe, that's going right now on Jupiter, so it's making a lot of measurement about magnetic field and so forth. But what it's also doing is measuring gravitational moment to try to decide what's inside of Jupiter, how Jupiter formed in the solar system. And one of the data, so you see we have a lot of data coming out right now on the solar system that are going to come in the next year, and that are concerned with the formation. One set of data, those are expensive satellite mission that we send to space. A lot of information that's, I think many times understated, is the isotopic measurement of meteorite. Meteorite as those rocks that come to Earth that we can collect and analyze. And right now, I think there is a lot of very useful data that are obtained from the isotopic measurement of meteorite, because measurements have improved now, so we can get more and more details in terms of the isotopic composition of those different meteorites. It gives us a good idea of the history, or better idea of the history of the solar system. And it doesn't cost much. You need to have people in the desert trying to collect those data and analyze them in the laboratory. So why we need so many data on the formation of the solar system? As I said, solar system are kind of odd architecture if you think about it and you try to simulate this dynamic, in a computer.
Yeah. You showed that previous slide.
Yeah.
In the lower right, you have this two ellipses, as if these are 2 separate groups. You call them
yes.
meteorites and non-carbon. Do you have any idea about why these are grouped like that? I know we have a couple of experts.
Yes. Yeah. So I could talk about it. What people are saying is, in fact, there's 2 families of meteorite. Is one coming of the outer solar system, one is coming from the inner solar system, and that came from the formation of Jupiter, the rapid formation of Jupiter that switched off the exchange of material within the disk and changed, in fact, the repartition of those.
We have 2 meteorite experts here.
Yeah.
Yuri and Trevor. Do you agree with anything?
That's what it's being interpreted.
Yeah.
All right.
If I say something wrong, just stop me. Yeah.
Actually,
now with still more data, and including data for the ideal contours, that dichotomy is becoming more diffuse. So there are more and more contours, for example, that fall between these two fields. So it may or may not be that clear distinction.
That's 20. That was 6 months ago publication, right?
Well, still,
But you have to all agree, you know, you have the meteorite. So, Klein Thorsten that I'm talking to, this is what he sent me for his meteorite, saying this is what you need to remember. He's the author of the paper, you know, that's why, that's his viewpoint. So anyhow, but I think it's important because people are tracing that to the formation of Jupiter. You know, people are saying we have those two reservoirs because Jupiter formed very fast into the disk, and this is proof of the timing of the formation of Jupiter. And while all those information on the formation of the solar system are important, is essentially since Laplace, we had a very simple picture in terms of formation of the solar system. You know, you have the collapse of a gas and star forming, you know, and slowly, you know, gradually you have the planet forming around that star with beyond the ice line. You know, that's why you had those big, you know, icy giant and giant planet beyond the ice line, and some very solid planet, metallic planet, you know, inside the ice line, and get your inner system. So people were, you know, that's what I learned when I went to school, and when I was a student, that's what was going on. And those two observations changed that simple picture very dramatically, because remember, you know, that quiet picture means roughly everything formed in 100 million years, and everything has been stable ever since for 4 billion years. So that's a very reassuring viewpoint on the formation of the solar system. So people made observation, and that's why when you make, you know, theory, we had one data point, the architecture of the solar system, we had a nice model, we were happy with it. New data, you know, observation of protoplanetary disks. So people are now able to image, you know, a planet forming, and so that disk, so those stages essentially, and try to have nice picture. And they see a very big diversity, and most of all, they saw that disks, you know, these don't disappear that fast. You know, these stay there and thus stay there for a long time. Second blow to that simple picture is the observation of the first exoplanet. Michel Mayer here with his big PEC 51b planet. You know, in the early 90s, he was applying for funding to try to observe exoplanet with radial velocity measurement. Didn't get any funding because people were taking those data, taking the solar system data, and they were saying there is no way you have sensitivity to detect Jupiter in a configuration like we have in the solar system. And he didn't listen to anybody, went to the observatory in the south of France, and he detected his first exoplanet. So it's a Jupiter-like planet, and the big surprise that came about is that's a Jupiter-like planet that's very close to its star. It's 10 times closer to Mercury and goes around the star in 4.5 days. And you see that when you have that data, suddenly you look back at your solar system and you say, well, there is something wrong with that simple picture where planets are forming slowly and they stay there for 4 billion years.
Can you just say he didn't have funding to do this?
He struggled, you know, because, you know, we have all those committees, we go in front of those committees and there was no what kind of result you should have. So anyhow, I'm glad he didn't listen to anybody and he could do his experiments. But I mean, it's something to be remembered in terms of predictive science. Yes?
I have a silly question about electrons. Would you want to be the first main sequence exoplanet discovered? Because there's also pulsar planets.
Yeah, but pulsar planet is not a planet, right?
This
You
is a
know?
cultural divide.
It's a pulsar, you know. You know, I think it was big news when he was a pulsar because that was the only one. But now that we have 4,000 planets, you know, I think we need to focus on the
The first main sequence planet.
yeah, if you want, if you call that the main sequence planet.
We use them as main sequences.
Yes. Yeah. But I think they are two different objects. That's why, you know, I'm saying it's not a planet.
I just want to like,
Probably it's a bit of something going on.
So if you want to give a new name to planets that are orbiting neutron stars?
No, I don't. That's why that's why I'm saying it's not a planet. You know. All right. Anyhow, don't distract me, Charlie. All right. Anyhow, so two observations that shattered that, very nice picture we lived with for many decades. So what that says is to have a Jupiter so close to your host star means that they are not staying where they form. And people very fast realize that the static solar system picture is not good, that giant planets migrate, when you still have disk and, they collide and with everything around, so they migrate. Second important point is the solar system is not stable. That whole thing is dynamically unstable. Jacques Lascar is one of the first person that pointed that out quantitatively, and I think he will give you a lecture during those 2 days. And so, theoreticians are pretty good. Once you have new data, we are always good at finding a new model that fits the new data. And that's what happened, in a series of two papers. There is a NIST model that came first in 2005, and you have the Gantak model that came in 5-6 years later. And this is currently the picture we have for the formation of the solar system. So here you have the time, million years here, about 500 million years, about 1 billion years here. Planet forming very close to the star, within 4 AU. They stay there for a while, then they start to migrate, your giant planet. So here you have, because it's inverted, so here you have Neptune, here you have Uranus, here you have Saturn, here you have Jupiter. So they form very close to their star. They start drifting, explaining why we have those giant Jupiter very close to the star. So they are close to 1 AU where the Earth is. Suddenly, because you have a resonance between Jupiter and Saturn, those two, so the fact of having two large giant planets, they get into resonance and Gantak. So if you do sailing, you understand what Gantak is. You go in one direction with the wind and you suddenly switch direction. And that's exactly what people think Jupiter and Saturn did, because they interacted together. They went back to a first position. So that's the Gantak model right here. So core formation, your planets are forming. You have your Gantak model where they are starting to get closer to the star. And because you had two giants, they turned back, went into the other direction, stayed there for 500 million years. And that's the instability. So that's the configuration you have here. I can get that started. You see, it never worked when it should work. We just tasted that. So anyhow, what you should see here, so you have those two planets nicely. Let me try again. Maybe if I do it. Yeah, because I've got many. All right, anyhow, so what you see here, so you have those 4 close-in planets. They stay there for several hundred million years, and suddenly, because it's dynamically unstable, they just change rapidly their orbit, bring all the debris around the solar system. That's the explanation for the late bombardment and all the cratering you have on the moon. And then it stayed there. After 1 billion years, they stayed there in their usual configuration. So you see, we are pretty far from our Laplace picture, because the planets that are here today, they formed there. They went around the solar system, gather material all over the place, and you see the solar system is more a shooting gallery than a nice, stable system staying there forever. So, two giant planets in resonance. So when you look at that picture, you say, well, the solar system is pretty odd. We need to have two giant planets, to have a Jupiter at the position is in today, and have an inner system with Earth-like planet. Without Saturn, Jupiter would have drifted toward this planet, and you wouldn't have any material left to form your terrestrial planet.
So,
yeah.
If we think about this in terms of angular momentum conservation, when Saturn and Jupiter are moving in, a lot of stuff has to be moving out.
Yeah.
And when they're moving out, a lot of stuff has to be moving in. Is that correct?
Yeah. Yeah. So that's what that movie was showing. This is the stuff. This is the planet forming. This is the green stuff you have around. All those rocks mixed. And the fact that everything is going in and out, that allows to understand why you can get some volatile, that form in rocks very high from the icy land, getting sometime, in the inner system.
So when Jupiter and Saturn were moving in, they were throwing a large amount of stuff out. Presumably, our solar system then threw out things like Oumuamua.
Maybe I think it did. When you had the late bombardment, I think it threw stuff in all directions.
What would be the late bombardment? Would
Yeah,
be when
in the late.
Saturn
No,
were
maybe
moving.
not in the beginning. I don't think so. Yeah, it's more when, you know, when it stays there for a while, and then when you have the NIST model, you know, it stays there and then oscillate, and then you have the late bombardment, and you have things thrown out of the system.
Since this is the first talk, we need to debug some things. Adam, could you try for about a minute to get this thing working? Do you think you can get it?
Let's see if it works on the second.
Go back and
Does the next one?
Let's see if this one works. Yeah, no. Yeah, this one works.
Do you want me to debug it?
So,
Or are you happy with that?
While I'm happy with that, we'll start with that. So what I was saying, so here is the first discovery of exoplanet. You know, the first exoplanet suddenly shattered our history of the solar system. So what have people been doing for 20 years in terms of detecting exoplanets? So right now, so there is 4 methods to detect exoplanet. I'm just going to talk about 2 because they are the 2 main methods that are right now used. So the first one is radial velocity, and the second one is transit. So what you have to remember is there is only a few planets, and it's in very peculiar situation where you can image those planets. When you talk about exoplanet, they are indirect measurement. And what you are looking at is, on one hand, with radial velocity, you are looking at the pull that the planetary system makes on the stars. So you're looking at the star bubbling because you have that planetary system going around. So you do spectroscopy, that movie here. If it plays again. So you see, you have the planetary system, and you see it's going to show, you know, the star moving, and that motion here you are detecting. So that's your radial velocity. By doing that, you get an idea of the mass of stuff that's going around the star. If you are in the right position, you know, from Earth, and you look at your different system, you can do transit. So there are many eclipses. And you see why it took so long to detect exoplanet, because as you can imagine, they are very faint measurements. So when you're looking at transit, best situation is going to be, you know, a very small diminution of the number of photons that come through the telescope. So those 2 methods right now, so when you do that, you get an information on the radius. When you do radial velocity, you get the mass. And combining those 2, you get the density. So what we get out of those 2 measurements for exoplanet is roughly the mean density for those objects. You have to remember, those 2 methods have biases because, you know, you are looking at some very small motion. You are geared toward detecting large planets close to their star. As I just say, mostly you get the density, and out of the density, by looking at what we have in the solar system, you can get an idea of the type of planet just by a density discrimination. Important thing is, out of those 2 measurements, you don't get the complete planetary system around each of those stars. You get a partial view of the number of planets that orbit some star, because the small planets are going to be hard to detect because you have a mean mass. And if you don't have the transit to confirm that, you're not too sure how many planets you have. The second thing is you have very long period planet orbiting the star are not going to be easily detected. And I think it's fair to say that right now, you know, with those 2 current methods, we are still not able to find the 8 planets, you know, around our own solar system. We won't be able to discriminate all those guys, mostly because it's limited in time. So first picture. So people have been working hard at making picture of exoplanets. So to be able to discriminate exoplanets, remember you have your star, very shiny. You have those small planets that are pretty close from their star when you look at them from the Earth. And so you are going to be able to do direct imaging if you hide the light from that star, and you are able to spot planets that are pretty young because they are bright. So you have a good contrast ratio, and that are pretty far from their star, much further away than the planet you are detecting using radial velocity or transit. So here is an example, the Beta Pictoris b, which is a very nice system you see here. So that's real picture throughout time where you are able to detect the planet. So here is the star that's hidden. You do adaptive optics. Here is your planet. You see, and you see the progress of the imaging in 6-7 years. And we're able to see Beta Pictoris because pretty big. From one end, it's 5 to 7 times Jupiter. It's on Saturn orbit, so you see very far out. And it's very young. It's a system that's about 50 million years. So remember, main thing to remember is when you look at exoplanet, you essentially are doing indirect measurement, looking at the biased view of exoplanet close to their star, and you have imaging. That means you can make spectroscopy from a few of them. And I'm not talking about transit spectroscopy. So you see, once we found the first exoplanet very close to their star and people knew where to look at, you know, suddenly it became an advantage. So right now, today, because we keep that number at my lab, we have 3,720 planets that are confirmed candidates. We have 2,787 planetary systems. Among them, 623 are multiple planetary systems. And so Kepler, here is, you see, before Kepler, we have the spot. Here is the direct imaging data, so I can give you some detail. This is the orbital period here, and this is the mass of the planet here. You have Jupiter, Neptune, the Earth, different methods, the transit and radial velocity. That's the two I talked about, direct imaging. And you see, keep that in mind. You have a few other complementary methods that are also used. So mostly those were ground-based measurements. And with the Kepler mission, you know, suddenly you were able to fill that gap, and you see now we are in a position where we can say you almost have a continuum. So you see Kepler is really biased. We're finding a lot of planets with orbital period of about a week, you know, around the different star, Earth-like planet, about different star, you know, with Earth here, still missing point. I mean, that graph is maybe a couple of years old. And you have a continuum between the Jupiter here and Earth-like objects. So one thing that's clear is there is a great diversity of exoplanets. You know, the first information we got is much more diverse than we initially thought, and it's really continuous. And right now, you know, big point is we have the density of those objects, and we're trying to do some spectroscopic data, and I won't talk about it, but I'm sure somebody will talk about it the next 2 days. Is we're starting to transit spectroscopy on some of those objects. So if we go back, so this is the exoplanet view, and now if we go back to our exobiology viewpoint, you know, is there life on those planets? That's what interests us. I know I missed my title. So among those 3,000 exoplanets detected, what we have is we have several Earth-type planets. So what we call Earth-type planets are essentially planets that have the same density, same mean density as the Earth. You see in that continuum, you have big giant, you have icy planet, and you have terrestrial planet. And of course, you know, one point I didn't mention up to now is those exoplanets are not detected around stars that are all similar to the sun. You have, you know, a big diversity of stars, and because it's easier because the contrast ratio is better, so it's easier to get planets around those little M dwarf stars, you know. So you have a gradation here in terms of the star diversity. So you see roughly here, so this is the exoplanet we think are terrestrial planet, and we call them in the habitable zone. They are essentially at the distance of the star where we think, you know, if you run a simple climate model, you can have liquid water on the surface. And those are different boundaries. So this is the Earth here. And you see if you get closer to your star, you are going to get runaway greenhouse and turn into a Venus. So that's not very relevant. And then if you go on the other end, you're going to start freezing and another greenhouse effect. So overall, you know, we are finding that there is about 20 planets that are called in the habitable zone. So they are planets that resemble the Earth in terms of density. They are varying mass in terms, they go from Earth mass to several times the Earth mass. And when you apply a simple climate model that's working on the Earth, you know, you can define them saying possibly they are in the habitable zone and they are habitable planets.
So what proportion of stars have planets? What's your estimate? Billions of star segments.
So how many stars have planets? I think the latest number estimate I've seen is 70%. Is that
70%.
yeah, 70%? Is that, would you confirm that?
No, Charlie has this.
I would say 100%, but what
Yeah, but I mean, I think that's what I've.
Should we make a bet on that? You say 70%, I say 100%, maybe in 10 years we can collect on the bet, but he's closer. How much of a bet?
If you want to get the last 10%, you're going to need to be able to detect exoplanets around these stars. And
Yeah, I think it's a detection issue. Yeah, I think it's more. I mean,
Stars are 2% stars.
yeah.
that would be, or it's more than 2, less than 10.
Anyway, continue, please.
All right, so whatever you say, Charlie. Anyhow, so we have planet in the habitable zone. So what do we mean, in fact, by habitable zone? What we do is we take a simple Earth climate model, 1D, that's what Casting did in the 90s, and you apply that to the various environment, roughly, essentially, to various different type of stars. And you can draw, so here is your, that's the mass of the star compared to the mass of the sun. So your M dwarf is very close here, and what we call the habitable zone. So the distance to the star where you can maintain, you know, an atmosphere. You're not destroying your atmosphere because you're either too close or too further out. You see that. So the Earth in the habitable zone, that's your habitable zone. So that's the distance to the star as a function of the type of the star. And you see that the smaller is your star, so the dimmer it is, and the closer you need to be in the habitable zone. So when people make big announcement on TV saying we found an Earth-like planet in the habitable zone, that's what they mean. They say, okay, we are finding planet, Earth-type planet, and most of the time they are very close to their star. They are around an M dwarf star. And when you do that, you are essentially like the moon on Earth, you are tidally locked to that star. So the notion of habitability is pretty weak because you're starting to have a planet that has the right luminosity and with the spectrum of the star could possibly maintain an atmosphere and could possibly maintain liquid water, but in fact, they are very different objects. So what we do when we say the main underlying assumption behind the habitable zone is you account for the varying luminosity and the spectra of your host star. But as I just said, when you are around those M-type stars, you are tidally locked, and it's a different object that you need to understand. The second pretty strong assumption, because it's really driven toward what we know on Earth, is you have the famous carbon silicate cycling, you know, so you're stabilizing the greenhouse effect like we have on Earth. You're stabilizing because you have volcano, you expel CO2, that's your greenhouse gas, and it goes back into the cycle. And at some point, you say you have some shale in the ocean, you know, that takes some carbon CO2 back inside the Earth. So you have two main greenhouse gases, you have the CO2, H2O, and that simple model were very useful in the 90s because it allows you to solve the faint sun problem and snowball Earth problem, because we know we had glaciation period throughout Earth history, and the effect that CO2 feedback loop, you know, at some point allows to regulate and maintain the Earth habitable, all right? Because you have that simple cycle that CO2 goes to the atmosphere, rains out, get back into the Earth, keep on going. And because we add that, somehow you regulate it and maintain the Earth habitable. Sorry? No way. So, initial ingredients. So, when we start thinking about habitable planet, well, it's because Charlie interrupted me.
Now I know why you wanted the longer coffee.
Yes. So now when we start thinking about habitable planet and finding habitable planet, you see that habitable zone argument is really driven toward what we know on Earth, and we need to think about it in very broader sense. So if you look at the history of, you know, you need to think to build up an habitable planet or inhabited planet towards the end, you think about the initial ingredients. So terrestrial planets are make up in the context of the history of the solar system. And that's what I was mentioning at the beginning toward your meteorite. We know that Jupiter has a very strong effect in terms of the delivery and scattering of elements in the solar system. And you have to wonder, in a system where you don't have a Jupiter, what type of initial building block you are going to have in your terrestrial planet. You know, are you going to have the same amount of volatile? Are you going to have the same amount of ices? So we need to think about the role of giant planets, because they also produce the late bombardment and bring about volatile in the solar system and in the inner solar system. So you need to think about the building block of your terrestrial planet in terms of the formation history, the late impact, you know, to get an idea of how you created your primitive atmosphere from the accretion of those various embryos. And one thing we didn't talk about, but we have another particularity in the solar system is you have the moon, which is a big satellite, one of the biggest satellites of the solar system that's orbiting the Earth. And we think at the moment that the moon formed after a huge collision with the Earth. And if you form a primitive atmosphere, accreting all that material that was around, so you're going to have some, probably maybe some water and hydrogen and helium, that moon impact is going to reset that atmosphere. And in a way that we are not too sure to understand. So you see, to just take the casting model in terms of what we know of the solar system history and those two particularities, make you wonder about how realistic it is to use that systematically for all different exoplanets. So when you think about habitable exoplanet, and that's what you are going to have talked throughout the coming 2 days about this point, is you talk about atmospheric evolution. So you want to go beyond that 1D model and get an idea of how that atmosphere is going to remain stable. And you have to think about varying composition of water and CO2 and maybe methane at some point. So you need to account for your stellar type and the activity of that star, because we know the M star. I will take another 5 minutes, you know, stop waving. Maybe another 10. And another important point on those climate models, you know, if you go beyond that 1D and do 3D climate model, you have varying landmass. And the only data we have is the data on Earth. The early Mars is an important source of data set, because we think initially we had some water and some atmosphere going on Mars. So the history of Mars is important to constrain that model, as well as the Venus history. But when you think about that simple model that casting put forward, you know, with the silicate carbon cycle, it means that you don't need to worry about your atmospheric evolution. You also need to worry about your geological activity. You see your silicate carbon cycle, and when you do that, you assume you have tectonic. And to have tectonic on a terrestrial planet is not something that's obvious. You have the exoplanet that are detected, the terrestrial exoplanet that are detected in the habitable zone, have varying mass and density. It means they have different mineralogy and different plasticity for their mantle. And there is no good reason for me to think that you are going to have systematically tectonic, and for how long you are going to have tectonic. And something that's pretty important too is you have varying land to ocean ratio, and that's going to also perturb your silicate carbon cycle. So those are two key ingredients that we use in the casting model to define what is an habitable zone, and they are very strong assumptions. The third one, and that's where we get into origin and biology, which is pretty important also, is the appearance of oxygen. You know, if we take the Earth's history, we don't think that oxygen was there at the beginning in the atmosphere, and we went on Earth from a transition from a lifeless planet to an inhabited planet. And if we look at the record of the Earth's history, we know that oxygen started to appear about 2 billion years ago, started to saturate the ocean, then saturate the... I'll fight against that. So saturate the landmass and then saturate the atmosphere. So you have the great oxidation event, and that's the third component that's going to change the composition of your atmosphere.
Who applies that? Remember?
Deadlines, 2014.
Okay. So that's the third important point. So that brings me to, you know, the exobiology part. You know, how do we get from transition from lifeless to inhabited? And that's a big chemistry and biochemistry question. You know, how did we get from there to there? And main question is, what are the required conditions? How probable is that event? What are the key transitions that led to complexity? And people are looking at different ways. Emergence of life at the chemical level. So at some point, you need to assemble molecules and get them started. You have transition toward complexity. And something we talk a lot about in the media is the feedback on the environment, because all that biological activity feedback stuff into the atmosphere, and that atmosphere needs to stay in equilibrium or unstable equilibrium. So the emergence of living matter, you had that famous experiment in the 50s where, Miller was able to produce several amino acids by reproducing what he thought was the primitive Earth in terms of atmosphere, and put it, electricity to simulate the storm. And he was able to create 20 different amino acids. And people in the 50s and 60s said, okay, we found the way how the life started on Earth, and which is essentially trying to build, existing biomolecules, so RNA and DNA, starting from those basic constituents. The problem is, 2015, you see that's one of the publications with John Sutherland, where you can find a common origin to RNA and proteins. And you see it's a real maze. So people right now are not succeeding, I think, are producing living matter from scratch in the laboratory, and they are pretty much lost in the biochemical maze. Each time you have a biochemical publication, that's what you need to figure out. And if it's that complicated, the cooking book, to get life started on Earth, maybe we need to think slightly differently. So some people are trying to do that in Paris, an alternative, which is more a physical viewpoint instead of biochemist viewpoint, which is to say, what's the recipes to make life? Some people are asking the question in a very different angle, saying, let's try to see if we have conditions that simulate, self-replication at the chemical level. So do we have conditions in terms of density, temperature, and atmosphere that's going to get started, the autocatalytic process that's characteristic of life? So you have your primitive chemistry, and suddenly you have the right condition and the right out of equilibrium condition to get the emergence of replicator. So there is two types of platform that's going on right now, because you can start talking about it in the classroom, but it's better if you do experiment. And people are trying to produce, a generic evolutionary protocol relying on temperature-induced gradients on one hand, and the other hand, which is, I think, is pretty nice, is to look at the emergence of elementary life-like property doing microfluidic experiments. So you can, put some formose reaction in those little bubbles, and you can spread them and simulate some replication and try to see if you have the Darwinism or Darwinian property emerging at the chemical level. And so that's a different approach that you need to have in mind. I think that's maybe as relevant, instead of looking at the recipes that led to life on Earth, is to look at conditions that led to life on Earth, which is a different paradigm that I think might be even more useful when you look at exoplanetary science. So we know that sustainability leads to complexity. I like that cartoon picture here where you have the bacteria, here you have the time scale. So you have the circle that gives you time scale. And when we look at life on Earth and trying to see what kind of influence is going to have on your atmosphere, that's what you're interested in when you do exoplanets. So you have your bacteria that started almost as soon as the Earth stabilized just after the late bombardment. We have trace fossil of that. And it went on for a while and suddenly become very complex. And sometimes we are overlooking, we are blinded by that complexity, thinking, if you're looking at aliens, you are somewhere around here. So we are more concerned with that question, that huge complexity. And this is the real tree of life. People are doing metagenomic and genomic analysis, and you see that bacteria that has been there for billions of years, very important diversity. And that's maybe when we look at life on other planets, that's where I think we should be concentrated on. So all that to say that from, for exoplanetary science, what's very relevant, in my view, is to try to understand major evolutionary transition and the impact it has on the atmosphere. If you have the chemical environment, so the condition that led to some self-replication, you have your Darwinian replicator, that thing is going to keep on going, and that's what you want to see. You want to see the effect on the environment at the planetary scale, because that's what you are going to be able to detect. We can speculate whether we have life on Encelade or we have lives, deep inside planets, but at the end we won't be able to detect it. So you won't have data to confirm or infirm whether it's right or wrong. What we can hope to have is to have spectroscopy of the atmosphere of exoplanet and to have data that's going to give you an idea of what's going on at the biological level. So in my view, when you're looking at biology, the relevant question is not whether, the relevant question in my view, and that's a cartoon I took from one of Charlie's paper, is to be able to model the emergence of ecosystem and the coevolution of life and planet habitability, because that's what's going to be the thing you want to measure from spectroscopy of exoplanets. So that's what you turn, you detect inhabited Earth-like planet on Earth. We talked about habitability. So you have a planet where the atmosphere is such that you keep liquid water on the surface. If you go the next step further, and if you look at inhabited planet, once you start to make those spectra, you need to be able to decide what's the signature of life on that planet. And that's something, that's an open game. We say if it's habitable, if we detect H2O, CO2, CH4 shouldn't be there. But if you have CO2, H2O, you can think that you have some cycle that gives you a stable planet. If it's inhabited, oxygen might be a sign of it, but maybe not. The combination of CH4 or O2 may be a way to go. What you need to keep in mind is what is the signature of inhabited planet is still an open question. I like what Lovelock said, in the 60s, that we should be looking at stars that shouldn't be there. I think right now that's maybe the best approach. We need to look at things that are in severe out of equilibrium and that we are not expecting. And that's more or less what would happen on Earth. So if you look on Earth, we don't expect to see oxygen if you just look at the formation and biology. So that may be the right way to go. But I think the next years are going to give us some more ideas because, we have many upcoming observational programs. So in the next 10 years, we are going to get better idea of the diversity of the atmosphere of those exoplanets, and this is going to change completely our picture, and we're going to get better idea of what we are looking at. All right, so that's what I wanted to say. So exobiology, I think it's a really comprehensive science. It touches very different fields from astrophysics, geophysics, biology, and chemistry. To use the solar system data, this is something very important. You always see when you talk about habitability, you really use the Earth-like model that you extrapolate to exoplanet, and that's something that's very important. We need to use all the data of the solar system to project what we think is happening on those exoplanets to build a comprehensive scenario where we will be able to identify habitable planets. So we don't need to invoke alien when you talk about exobiology. And we have to be careful, when we talk about formation, we are really focused also on what we know, and this is the solar system architecture and all those particularities. And if we are not careful, we fall into those particularities and turn into the rare earth hypothesis, which is close to a religion, if we push it too far. All right, so sorry for being long, but that's because of Charlie.